All right. So you all should be able to hear me and see me as well as the slide on the screen. So I'm going to go ahead and get everything kicked off. Before we begin, just a couple brief announcements. And that's typically how I'll start all my lectures is right before we get into the topics. I'll take a minute and just discuss a couple things. First off, I wanted to mention about Friday's lecture. I had a death in the family a few days ago, so I won't be able to be here for the stream on Friday. Friday's lecture will be a recording. What I'm going to do is I'm going to record that lecture through Blackboard, specifically through that test debug channel that's listed on the on Blackboard Collaborate. And so I might do that sometime tomorrow. So I'll probably just log in and do the lecture. So if you happen to see me access that, or if you get an alert that class is open that day, don't worry. I'm just recording the lecture to make up for Friday. I'll let you know when that is active and available, probably through Microsoft Teams. But we won't meet as a class on Friday because I'll be attending that funeral. I wanted to mention a couple of other things. First off, you all should have gotten a message on Microsoft Teams that the recording from Monday has been uploaded to our YouTube playlist. I decided to send that message through Teams to make sure that everybody saw that in Teams. If you haven't, I would make sure that you've downloaded Teams and that you've installed it to check and see that you can access that. And if anybody has any questions, you can contact me by email. But I would make sure that you can see that. Lastly, in case for some reason I'm not able to access or upload the recordings immediately, I wanted to show you how to access them and collaborate. To be honest, it's not the easiest thing to see. But if you go onto Blackboard Collaborate, if you look in this image here on the top right, the upper image, on Blackboard Collaborate, there's a black bar and there's these three horizontal lines. If you see that, that's the button that'll open up the menu. And when you open that, you'll see the recording slot. It's not the easiest thing to find the first time you're looking for it. So I wanted to make sure that everybody was aware of that. Lastly, we are going to have our first homework assignment assigned today. It'll become visible on Blackboard at 2 p.m. after class, but I'm going to show you the assignment here in a bit so that everybody sees that. But I just wanted to make sure everybody's aware, and that's going to be due Friday. Any questions before we get this kicked off? All right, and again, if you have questions throughout lecture, don't hesitate to, you can either use the raise your hand feature, you can use your microphone to ask, or you can put them in the chat, whichever works. I'm easy to get along with. Please, any questions you got, don't hesitate. Will the Friday lecture be in the recording tab on Blackboard? Yes, and my plan is to also put it on the YouTube playlist. What did you say will be due Friday? There's a homework that's going to be assigned today. It won't become visible on Blackboard until 2 p.m., but I'm going to pull the homework up at the end of the lecture so that you all see. Sound good? All right. What we're going to do today is we're going to do two things. We're going to do a very brief review of physics, and then we're going to talk about units, which is one of the big components, not just of this class, but of engineering in general. And so I want to talk about physics, and I want to talk about it at a super high level. One of the questions that we got on Monday was, well, what happens if we haven't had physics? Are we going to be at a disadvantage here? And the clear and resounding answer to that question is no. But what I want to do is I want to cover the very, very base level of physics that I want everybody in here to be aware of. But we're going to keep it super basic. I'm actually going to stop the screen share because I want everybody to see me and to see the whiteboard. I'm actually going to use the whiteboard here for a quick second because I want to introduce a couple very, very basic concepts. Okay, so let's just look at some super basic examples in physics. And we're going to start off with the concept of velocity. And don't worry, everything that I'm putting here on the screen here or on the board here is reflected in the slideshow. So if there's something that you miss or whatnot, that's no big, not really that big of a deal. I'm gonna have to get used to standing on this side of the board so that I'm in the camera view. So let's start off with something really basic. Okay, let's say that this is point A, and let's say that this right here is point B. Okay, and let's make up a distance between them. Let's say that this is 20 feet between here. Okay, so it's 20 feet between point A and point B. And so let's say, I have this taped out on the floor and I walk from point A to point B. So here's me. Please forgive my work. And I walk from point A to point B. And so when I start walking, I hit my stopwatch. I say go, and I walk and I walk and I walk and I hit stop right when I hit point B. And so let's say that took 5 seconds to get from point A to point B. And so what I might say is, okay, so let's say that X is my distance, or maybe another way of putting that is position. And let's say T is time. Okay? Which, by the way, if for some reason this isn't legible, or if there's something that you don't, or it isn't coming clear through on the camera, please put it in the chat. I'll be happy to rewrite or write something bigger. Please, I want to make sure this is clear for everybody. And so what I might say then is, okay, I look at this problem and I say that, well, my change in position, and those of you who, everybody calculus, so you're probably familiar with notation like this, where, delta, the triangle, capital letter, Greek letter is the symbol for change. So my change in position might be 20 feet, and then that occurred over a change in time of, let's say, 5 seconds. And so therefore, my velocity is the change in distance over the change in time. And so that's basically what velocity is. It's just how far you traveled over what period of time. And so if I traveled 20 feet over a time period of 5 seconds, that would be 4 feet per second, just 20 divided by 5. Everybody with me so far? That should be pretty basic. Okay, and so this would be sort of a basic concept of velocity, just change in distance over change in time. Now, everything that I'm doing here is algebra based. Okay, now everybody in here that's had calculus knows that what calculus can handle that algebra can't is not just average change in average rate of change, but instantaneous rate of change. So the calculus-based definition of this, instead of looking at the change in position over time, we would be looking at it from a calculus standpoint and saying that velocity would be defined as the derivative of position with respect to time. And so that, in terms of physics, super in-depth physics review, we're kind of halfway there with that point right there. That velocity would be defined as the derivative of position with respect to time. Okay, and so that's velocity. Okay, now right off the bat, I'll mention that I'm probably using I'm saying the word velocity, and based on this notation, the term velocity and maybe even the term speed, I could use the term speed and velocity interchangeably. There is a difference between those two terms, and that'll become clear sometime next week when we start to introduce the concept of a vector. But for the purposes of discussion, we can just say that velocity is the derivative of position with respect to time. I'm going to leave this up here for a sec in case anybody's writing this down. I'll leave this up for a sec, and then I'm going to erase. I'll give everybody a second. Let me get out of your way. Keep in mind, I'm also recording this, so if you need to, if you miss something, you can always pause it and come back. Okay. All right, so I'm going to go ahead and erase this. So. All right, so velocity, we can just rewrite that as the derivative of position with sorry, with respect to time. Okay, now, what about acceleration? Everybody has heard of this concept before, particularly when you're looking at like maybe sports cars or something. Like you buy a car and they say it can go from 0 to 60 in so many seconds. Well, that's what we're talking about, is a change in velocity, right? So if we're talking about a vehicle, let's say 0 to 60 in, I don't know, 5 seconds. So it goes from not moving at all to moving at a speed or a velocity of 60 miles per hour over a period of time. So we're talking about acceleration as being the rate of change of speed. Or now look at what we've got going on here. We've got velocity is the derivative of this, and acceleration is the derivative of velocity. So if we wanted to get, sorry, that needs to be an X. If we wanted to get, I guess, fancy, we could write it like that. Okay. If you understand that, that is about that's about 80% of all the physics that you really need to know. And honestly, we're not even going to really do any problems in this course where we evaluate this stuff. This is really just from a conceptual standpoint. Okay. Let me pull back up the slide, because the slide that I was on really illustrated a lot of this here. I just kind of wanted to walk everybody through it. So let me go back to this. So this was the slide that we left off on, and let's go to the next slide. And so this is really what we're talking about. So what I have on this slide is consider an object moving in space for some time. So x would be its position, or the distance, if you will. And so velocity is just the rate of change of position, and acceleration is the rate of change of velocity. Okay. And the reason why we're talking about this, it might seem a little counterintuitive, because this is statics. We're talking about bodies that don't move. So why are you talking about velocity and acceleration? Well, that'll become clear here in a second, because long story short is we use acceleration in combination with mass to define forces, and forces is really the biggest part of this class. The only other thing I want to point out on this slide before we move on is this notation. So if you look at the slide, you'll see that certain letters are bolded and some aren't. So for instance, you'll see that x, the x, the velocity, the acceleration are all written with bold letters, and everything else isn't. Why am I writing those terms with bold letters? There'll be more on that later, but the long story short is that anything that's written with a bold letter is a vector. Okay. If you open up your textbook and start flipping through it, you will see all sorts of problems that are being done, and you'll notice a lot of terms being written with bold letters. Those are vectors. But don't worry, we'll dig into what vectors are in very significant detail later on. Everybody with me so far before I move on? In terms of math, that's probably the most rigorous thing we'll talk about today. Good deal. And again, if you got any questions, please don't hesitate to ask. Okay, now we need to discuss the laws that govern motion. And what I'm starting with are Newton's 3 laws. Now, whether or not you've had a course in physics, I got to believe that just about everybody in the class has at least heard of Newton's 3 laws. Well, I want to go through those laws in specific detail one at a time, just to make sure that we're all on the same page. So let's start off with Newton's first law. An object that is at rest or in motion will remain at rest or in motion until acted upon by an outside force. So basically what that means from a statics perspective is that we start off with a reference frame, assuming that all of our bodies have a reference frame of 0 force. So here's this calculator. We start off with 0 forces, and then what loads are being applied to it. Second law, and this is where all of this stuff that was on the board came into play. The second law of motion is really where the definition of force comes from. So we have a mass undergoing an acceleration, mass times acceleration. that's where we get the definition of force. An object's rate of change of momentum is directly proportional to the applied force. And so that's where that definition of force comes from. In statics, we really don't deal with velocities or accelerations all that much. But forces, buddy, we deal with forces a lot. In fact, you could argue that statics and dynamics is just the study of forces and how they affect bodies, whether or not they're all acting, at a common point, or whether they're acting in all sorts of different directions, whether the object is moving, whether or not it's not. It's all about forces. And so after today, or really after next week, that's pretty much all we're going to be talking about is forces for the remainder of the semester. And one of the most classical definitions is force equals mass times acceleration. That comes from Newton's second law. Third law: all forces between two objects exist in equal magnitude and opposite direction. And that's an incredibly important law that we're going to be using throughout a number of things that we do in this class, from determining reaction forces to determining internal responses when we cut sections. That's going to be a very important aspect of our work. For instance, we cut a section, we look on one side of the section, the force is acting upward, and on the other side of the section, it's acting downward, equal magnitude in opposite direction. You have a point that has a series of forces on it. That resultant might be acting this way, the reaction force is acting equally and in the opposite direction. That maintains static equilibrium. Don't worry, we'll get through all of that in very significant detail as we move throughout the semester. Now, I want to talk about this other law. I mean, I'm sure that there's some physicists that are going to hate me if I call this Newton's fourth law, but this is another principle of mechanics that becomes very important to us, and we're actually going to use this law very frequently throughout this course, although we use a very specific aspect of this law, I guess I should say. And it's Newton's law of universal gravitation. And so what Newton's law of universal gravitation states is that, let's say I have two objects, and it doesn't really matter what those two objects are. Let's say they're, this coffee cup and this marker, okay? This coffee cup and this marker each have two different masses, which I'm using the term mass. Maybe I should define that, a bit more rigorously. Mass would be a numerical quantity that defines the amount of matter in these objects, and there's a very specific distinction between an object's mass and an object's weight, which we'll get to here in a second. So, but let's keep it on the terms of mass and matter. I've got these two pieces, the coffee cup and the marker, and let's say they are separated by a distance r. So here's m, the big mass, the little mass, and they're separated by this distance r. Newton's law of universal gravitation states that there is an attractive force between those two objects, and this is true for every object in existence. Now, to be fair, we're talking about a coffee cup and this marker. These two objects are incredibly small, and when you look at the universal gravitational constant that goes into that relationship, it's this results in very, very, very tiny forces. And that's true. It's not like I have a coffee cup and a marker, and if I put them in the same room, they suddenly smack into one another. It doesn't work like that. But there is a force. It's just incredibly, incredibly minuscule. Where that comes into play, though, is when we're talking about objects that are very, very, very big, like the Earth. Okay, so let's apply the law of universal gravitation to what we're talking about on the Earth. Now, let's use another example. Let's say that I've got these two objects in my hand. Now, these two objects in my hand are two markers. For the sake of discussion, let's assume that they are identical markers. So they have identical mass. They have the same amount of matter in this marker than in this marker. Okay. Well, you've probably heard this before. Well, why is it that this marker weighs less on the Earth than it does on the Moon? Well, they might have the same amount of matter, but they have a different weight. The reason why is because the two objects that are attracting one another, it's a different scenario. Here, if I take this marker and I let it go, it's going to drop and hit the floor. The reason why is because there is an attractive force between this marker and the Earth. Okay, Whereas if I have this marker on the moon doesn't have as much mass, so that attractive force is less. That's why when you're on the moon, you're a little, your weight is decreased because that attractive force isn't as much. So we rearrange that formula a little bit, and we can develop a relationship between the mass of an object and the object's weight. And the relationship between an object's mass and an object's weight is that the weight equals the mass times this little term g. And all g comes from is just that original law rearranged a little bit. And what is g? G is an acceleration, specifically the acceleration due to the gravity of Earth. Okay, so in order to determine an object's weight, we take an object's mass and we multiply it by the gravity. Now, if you look at what defines the acceleration due to gravity, technically this would depend on where we are on the Earth, right? Because what defines that attractive force is the radius between the two forces. Well, technically, I guess my weight is going to be different in, say, Huntington, West Virginia, than it would be on Mount Everest, because I'm further away from the Earth, so the weight would change. And that is technically true. But we're talking about engineering, we're talking about civil engineering applications, and I don't know that I'm going to be building any bridges between Huntington and Mount Everest anytime soon. So for the purposes of discussion, I can just use the same value for G that I use in any problem that I deal with. The term G has different quantities depending upon what unit system you operate in. When you graduate with an engineering degree, there are certain numbers that should just be burned into your memory, by the time that you get out of here. And two of them are these numbers right here. So the acceleration due to gravity. If we're operating in SI units, the acceleration due to gravity is 9.81 meters per second squared. And again, it's an acceleration, so it's a velocity meters per second, but then it's per second, the change in velocity per second, hence why it's meters per second squared. The acceleration due to gravity in SI is 9.81 meters per second squared, and in US units, it's 32.2 feet per second squared. So if there's any two numbers that you kind of want to just burn into the back of your head that I must commit these to memory, it would be these two numbers. Now, before I move on, are there any questions about the physics I've discussed, about anything that we're talking about? I'll give you a second to process. Good. How's that? Wait. Was this the slide? All right. Anybody else? One other thing, by the way, if you go into course content, I have uploaded these slides. So all the slides are on Blackboard, and I'll do that throughout the semester. I won't, keep these to myself. They're already posted. But yeah, don't hesitate to ask stuff like that. That's why we're here. All right, everybody good? All right. Okay, let's talk about unit systems. Okay, and basically what we're talking about is do we operate in metric? Do we operate in US units? Do we, how do we convert between them? And I want to discuss something called dimensional analysis. Now, if you had Engineering 111, you probably discussed this. I'm not sure in what detail you discussed it, but I do want to cover some basics of it. To be honest, one of the benefits in this course is that the unit conversion issue and converting from one system to another is not as big of a deal as it is in some other classes. But I do want to make sure that everybody's familiar with the various prefixes and the unit systems, just so that we're all on the same page moving forward. So let's look at some standard units for mechanics. What I have here is the base quantities that we're going to be using in this course. And even looking at this, a lot of our problems are really going to be dealing with force and length. Like those are probably the most important. Every now and then, we'll have to convert a mass to a weight, which is probably of all the slides that I discussed previously, if there's any one formula that you'd want to take away, it'd be the conversion between mass and weight. Weight equals mass times gravity. But if we're talking about, physics and mechanics related problems, these are the quantities that we are dealing with, like length, time, mass, velocity, acceleration, force. And these are the basic units that we're going to be dealing with in engineering. And so if we're talking about SI units, the base unit of length would be the meter. The base unit of time would be a second. The base unit of mass is a kilogram. And so we would express velocity in meters per second. We would express acceleration in meters per second squared. And then the unit for force, we have a name for that. We call it the Newton, pretty apropos given Isaac Newton's 3 laws of motion. And a Newton is defined as, remember, force equals mass times acceleration. So a Newton is 1 kilogram times 1 meter per second squared. That is the definition of a Newton, okay? In US units, what is our length unit? And look, let's sort of have this one discussion right now. It's like, which unit system is better? We could debate the merits of the SI system versus the US system any day of the week. As an engineer, though, the honest truth is, and this is particularly true for civil engineers, you kind of need to navigate both. Until I can go to Lowe's and look at the shelves and see only tape measures in metric, we still have to be able to operate in US units. Civil engineers operate in the construction industry, and in the construction industry, they use feet and inches. So we have to be able to operate in that system because that's what we use. So I do think it's important that you're able to assess both. I'd say the standard unit of length in US units is the foot. You could argue it's inch, but either one would probably be acceptable. The unit of mass in US units is what we call the slug. So in US units, we sort of, there's a little bit of an opposite between SI. In SI, we have a standard unit for mass, which is a kilogram, and then the unit of force is defined based off of the mass unit. So a Newton is a kilogram times a meter per second squared. Whereas in US units, the standard unit is the force unit, the pound, and then we define the slug as a pound divided by a foot per second squared. So just be aware of that. In all honesty, though, we really aren't going to have to deal with those types of conversions too much. That's going to be, for the most part, a pretty straightforward process. Just wanted to lay that out for everybody. Let's talk about prefixes. You've probably seen this table before, or a table like it that lists all the unit prefixes, but the ones that I have highlighted here in yellow are really the ones that you're going to use most often as an engineer. As a civil engineer or mechanical engineer, I have used the micro term, I've used milli, I've used centi, I've used kilo. I really haven't used the other prefixes very much in real life settings. I mean, granted, like hard drives, there's a terabyte and a gigabyte and a megabyte and all of that, but I haven't really, operated in terameters or something like that, or femtograms or something. As an engineer, I've really never used those. The ones in yellow are the ones that I've used, regularly, and so as a practical matter, those are probably going to be the only ones that you really need to remember. There are a couple units that I want to mention. First off, inches. You're going to, as an engineer, you're going to use inches, and so just make sure that everybody's aware of that. They're widely used in civil engineering applications. One other civil engineering applications, which you may not have heard of yet, but I promise you will become widely used in a lot of my courses later on in structural engineering. You'll use them in probably geotech and some other disciplines, is the KIP, K-I-P. KIP is shorthand for a kilopound, and so 1 KIP is 1,000 pounds. We use KIPs quite a bit in civil engineering to simplify a lot of the calculations that we do. So for instance, I'm here in my office, and right here is a column that is being used to support this exterior wall. if I was designing that column, I would probably determine the number of kips on that column. That column is holding up 92 kips, and then I would size the column accordingly. Kips are very, very common in structural engineering and civil engineering applications. So that's a unit we're going to use quite a bit in here. So what I want to do with you all right now is go through some unit conversion examples. Now, I'm sort of jumping right into this because you all should have had some experience with this in some of your previous courses, but we're just going to go through this together so that we're all on the same page with how to do this. And I want to also be clear, I'm not one of those professors that you must do it my way. There's a number of different ways to handle this, just as long as you're ultimately documenting everything appropriately and that you're getting the right answer. So we have two quantities that I want to do a unit conversion on. I want to convert 73 miles per hour to meters per second, and I want to convert 63.9 psi, or pounds per square inch, into kilonewtons per meter squared. You could also call that a kilopascal, but I'm actually writing it this way so that we can track the unit conversions. So what I'm going to do is I'm actually going to stop the screen share. But before I do, one other thing. On the top right, I have some unit conversions here that we can use for this problem. And I'm going to stop the share, but I'll show you where these come up here in a second. Let me stop the share, and then let me share my screen. So there's probably going to be some cascading here in a second. Yep, there's the cascading. Okay. All right, let me pull up the OneNote. Okay, so let me move this down. Oh, goodness. Actually, let me just unplug this. Okay, so our first quantity is we're going to convert, it was 73 miles per hour equals some quantity in meters per second. And so we're trying to figure that out, okay? So the way I like to do this is, first off, whenever I see one of these like mile per hour, one of these shorthand, I always like to write it as a fraction. Which, by the way, I am going to be calling on chat here in a second to help me out with some of these unit conversions. Everybody get ready. And then the way I like to handle this is I like to start multiplying this quantity by fractions. And I write the fractions in a very specific way. For example, let's take this term hours. Okay. So one of the fractions, and I'm just going to go ahead and do this first one on my own, is I'm going to say that 1 hour is 60 minutes. Okay. Now I wrote this fraction in a very particular way. The first way is look at the fraction. I have 1 hour on the top and 60 minutes on the bottom. Well, 1 hour equals 60 minutes. Okay. So when I divide them, if I have 6 equals 6, well, what is 6 divided by 6? It's 1. So this fraction has a meaning of 1 because 1 hour equals 60 minutes. So whenever I multiply this term by that fraction, I'm not really changing it. If I multiply something by 1, I get the same answer. So that's everything that's in that fraction. The top has to equal the bottom. Now I put the hours on top because what I can then do is cancel the hours. If I have a term and I have a term on the top and term on the bottom, that cancels. And so what I then do is I just keep doing that, and I just keep on doing that until I've gotten to the units I want. Now, if I were to stop right now, I would get an answer that's in miles per minute, but that's not enough. Okay, I need it in meters per second. So let's convert that minutes into seconds. So now I have miles per second. That's exactly what I want. And now what we need to do is we need to get that miles into meters. Okay. Now the slide listed the conversion factor between feet and meters. So probably what I need is I need something that will convert feet into miles. Now I'm curious in chat, does anybody know how many feet are in a mile? There we go, 5,280 feet, exactly right. So 5,280 feet are in 1 mile, exactly right. And now we can convert our feet and so I can use the one that's on the top of that slide that states that 1 foot is 0.3048 meters. Okay, now what I want is I want somebody in chat to plug and chug all of this out. So what you're going to do in your calculator is you're going to take all of these numerical quantities. So it's going to be 73 times 1 times 1 times 5280 times 0.3048 all over 60 times 60 times 1 times 1. So you could ignore the ones. You don't have to throw that into your calculator. And tell me what you get for an answer. And for the sake of discussion, let's just do 2 decimal places. So what are we getting here? There we go, exactly right, 32.63. So this is 32.63. So this is 32.63. And let's just check and make sure our units came out the way we wanted it. So we've got the minutes canceling. We've got the feet canceling. We've got the miles canceling. And so all we're left with is meters and seconds. And that's what we wanted. Pretty simple, pretty straightforward. Any questions before we move on to the next one? I'll have to get used to the cascading. That's a bit weird. All right. This one is 63.9 pounds per square inch. So it's pounds. Now, the notation that I have here, it's LB sub F. That just indicates that it's a force. Sometimes you'll find the notation is LB sub F for force and LB sub N for mass. So if you ever see the term LBF, that's just, you know, hammering it into you that it's a force. Per square inches equals some value in kilonewtons per square meter. Okay, now, so we have 63.9, and we'll say, make that a subtitle. Okay, now, let's start off with the force. So let's deal with the force first. So I'm going to start off with the term that was provided in the problem statement up top. And that said that 1 pound, make that a subtitle, is 4.44822 newtons. Okay. Now, that'll get me to newtons, but I'm going to ask the chat's help on this. Okay. So the answer needs to be in kilonewtons. Okay. Now, I'm curious. Do I divide by 1,000 or do I multiply by 1,000? I'm going to go to the chat and see. There you go. Yeah, you're right. Exactly right. You divide. Good, good. Okay. So, and then the way that you can do that always is just ask yourself, okay, here's the fraction. I need newtons on the bottom, and I need kilonewtons on the top. So how do I get there? Okay, well, the kilonewton is the bigger unit, right? So it's like 1 kilonewton is a bunch of these little newtons. So 1 kilonewton is 1,000 newtons, okay? And so now if we start using our cancellation, what do we have? We've canceled the pounds, canceled the newtons, and then there we go. So now we have kilonewtons per square inch. Now, so now we need to deal with the length, okay? So the problem provided a conversion factor between inches, or sorry, between feet and meters. So first thing I ought to do is probably convert those inches to feet, okay? So that's pretty easy. There's 12 inches in a foot, right? So 12 inches, put that on top, 12 inches and 1 foot, okay? Now, does anybody see a problem with this? Is there something I'm missing, something I'm forgetting here? Let me go to the chat and see. They're not squared. Exactly right. See, look at the bottom of the first term. It's square inches, right? When I just use this, I'm only converting once. So you can do this one of two ways. You can square it, or you can just do it again. That works too. And so now I know I've handled the inches twice because it's square inches. I converted one of them, and now I'm converting another. You can do it that way, or you could replace this with that. However you want to do it. There's no really wrong way of doing it, just as long as you're tracking both of them. Sometimes I like to write both just to ensure that I counted it twice. It helps me, remember it. Okay. Now we've got it in kilonewtons per square foot. Now we need it in kilonewtons per square meter. So I'm going to use that conversion term, that 1 foot, 0.3048 meters. But again, I've got to do it twice. So bam. And so now look at what, let's do the unit cancellation. Let's see what we've got. So 2 inches, 2 inches, 2 feet, 2 feet. And so I've got kilonewtons and square meters, exactly what I wanted at the end. Now somebody in chat, go ahead and chug that out, and we'll do the same thing. Let's just do 2 decimal places, and let's see what we get. I'll give it a second, then I'll pull up the chat. I can't, the way that my interface is set up, I actually can't see what's going on in chat right now until I pull it up. Once you see the screen cascading, then I can see what's going on in chat. We're going to pull it up. Boom. Exactly right. 440.57. I got 5.8, but that's close enough. .57 kilonewtons per meter squared. Later on in some of your engineering courses, you'll have a name for that unit, and it's 440.57. We call it a kilopascal. So the Pascal is the unit, the SI unit for pressure or for stress. Those two terms are interchangeable. You'll deal with that later. Okay. All right. All right. Does anybody have any questions? Do I need to go back to the slide? If not, I'm going to go ahead and move on. I want to cover something else real quick. Are we going to get a conversion sheet for exams? Maybe, but you probably won't need it all that much. And the other question I saw in the chat, will sig figs matter in statics? I'm going to be honestly, not that much. I'm not as big of a deal on it, especially in civil engineering applications. It tends not to matter all that much, especially when a lot of times we're building spreadsheets that do the math for us. Okay. All right. Can everybody see the the screen that you see here, or the dimensional analysis? Okay. I want to talk a little bit about what honestly is a bigger problem that I've noticed since I've been teaching engineering classes than significant figures, because we're talking about just the rules for rounding, and with enough time, you can memorize those. What is more important is understanding that the units are consistent. So, for example, I have a beam that is this is a very famous problem in structural engineering. This is the deflection of a beam. So I have a beam, it's simply supported, and I have a load in the middle, so I'm loading it. When you have a beam, it deforms, under load. How do we compute that deformation? Well, the formula for computing, and this is something that you'll learn when you take me for structural analysis, how to derive this, is PL cubed over 48 EI. Now, this is a deflection, right? So if it's a beam that's deflected, we want to know how much it's changed. That deflection should be in something like inches or feet. It should be a length unit. And so what you see here in the bottom is what's called a dimensional analysis. We're taking the input terms, the applied load that might be in pounds, and the length of the beam that might be inches, and so on and so forth. And hopefully when it's all said and done, the units come out the way that they should. This is, as a student, I've found that students tend to have a big problem with this throughout their courses. And so I want to exercise this with you with the following problem. This is the formula that you use to compute the total amount of energy in a fluid conduit, okay? So when you take fluid mechanics, you'll find that energy comes from three terms. It comes from the pressure head, from the velocity head, and the elevation head. And so that's those three fraction terms that you see in that formula. And so hopefully when I add those terms up, they should all be dimensionally consistent. And so I just want to walk through that with you very, very quickly. Let me just pull this up on the notebook so you can see. And this is a really, really simple problem. And if I go through this a little quickly, I apologize, but I want to show you something with our class notes here in a little bit that I think you're going to like. So the formula, hold on. Did my pen decide to fail on me? Uh-oh. My pen has decided to crap out on me. Whoop. We might have to do this one later on. We might have to hold off on this one. All right. Here's what we're going to do, because my pen has decided to crap out on me, and the last thing I want to do is hold you accountable for that technical glitch. Here's what we're going to do. Let me stop this real quick. Let me pull this up. Okay, this is your homework assignment, and what I'm going to do is this. I'm going to call an audible right now in your favor. Instead of having you be responsible for something that having you be responsible for something that I wasn't able to cover in class, there were two problems on the homework assignment. The second problem was going to be related to this dimensional analysis, but I didn't have time to cover it. What I'm going to do is I'm just neglect that. And instead, we'll have just the problem one be worth 10 points to make it a little easier. So we'll say problem one, 10 points total, 5 points each. And instead, what I'm going to do is in my recording for the lecture on Friday, I'll briefly show how to do this problem too. It's really, really straightforward. I think what happened is I think the battery on my pen died, and if I can't do the problem on the screen, then it'd make it a little difficult for you. But instead of holding you responsible for something I wasn't going to be able to cover up, we'll just push that off for later. Sound fair? Because I don't want to keep you longer than class, because I know some of you have classes after this. Any questions about the unit conversion stuff? No, it'll be due. That's a great question. When's it due? It's due at 1 on Friday, right before class. And that'll be how all my my homeworks are structured. They'll be due at 1 p.m. right before class starts the next day. So what I'm going to do is I'm going to redo this PDF. Any particular format you wish to do the homework in, just as long, if you remember what I mentioned on day 1, where the heading on the sheet, just have the name, the class, the homework assignment, the pagination, and as long as it's neat and legible, no. But yeah, what was in the syllabus and what we discussed on lecture 1, as long as you follow that, I don't really have any major issues with format. I do want it to be legible though. Make sure that it's legible and it's easy to see. Any other questions? All right, I'm going to redo that assignment and call an audible so that I delete that problem 2 instead it's only problem 1, and then we will we'll catch up on Friday. And again, I'm just going to record the lecture for Friday, and I'll have a homework on Friday due Monday. And with that, I will see you all on Monday. Hope everybody has a good weekend. If you need anything, don't hesitate to ask.